take that filtrate and change it to urine, and that's going to involve the other two steps: tubular reabsorption, where we're going to bring back most of the filtrate, and then tubular secretion, where we put some more stuff into that urine or filtrate that we didn't get on the first pass. So tubular reabsorption reclaims most of the tubular contents and returns them to the blood. There are some selective transepithelial processes, which means you go from one side of an epithelial cell to the other. Almost all the organic nutrients are reabsorbed this way. Water and ion reabsorption is hormonally regulated and adjusted. They will include active and passive tubular reabsorption. Substances can then go by two routes, either transcellular across the cell or paracellular around the individual cells. So here is our tubule with the capillary nearby, and we're going to put stuff back into those capillary beds. The transcellular route involves the solute entering the apical membrane of the tubule cell, travel through the cytosol of the tubule cell, and exit the basolateral membrane of the tubule cell. And it would then enter the blood through the endothelium of peritubular capillaries. The paracellular route would be between tubule cells. This is going to be limited because there are tight junctions, but in the proximal nephron it is a little leaky. And water, calcium, magnesium, potassium, some sodium in the proximal convoluted tubule can go this way. So you can get paracellular here. Transcellular, you'd be absorbed by the cell, make your way through the cytoplasm, and be released on the other side, and then you have to get to a peritubular capillary. We're going to walk through this. So transport across the apical membrane here. This is our transcellular route. Diffusion through the cytoplasm or cytosol, and transport across the basolateral membrane, which often involves lateral intracellular spaces because membrane transport ions into these spaces. So ions out here on the other side of the tight junctions. And then the movement from the interstitial fluid into the capillary. On the paracellular side, we would go sneak between the cells and move to the capillaries. Sodium transport across the basolateral membrane. Sodium is the most abundant cation in the filtrate, and transported sodium across the basolateral membrane of the tubule cells is primarily through active transport using the sodium-potassium ATPase pump to put sodium into the interstitial space, and then sodium can be swept back by bulk flow into the peritubular capillaries. Across the apical membrane, sodium is going to enter the tubule cell at the apical surface through the secondary active transport, and this would be a co-transport, or by facilitated diffusion through channels. So we actively pump the sodium at the basolateral membrane that results in a strong electrochemical gradient within the tubule cell. That results in a low intracellular sodium level and facilitates sodium diffusion and sets up a sodium gradient. Potassium leaks out of the cell into the interstitial fluid, leaving a net negative charge inside the cell. That also helps to pull the positively charged sodium inward. Sodium reabsorption by primary active transport will provide energy and a means for reabsorbing almost every other substance. So those would be called secondary active transports. So the electrochemical gradient created by the pumps at the basolateral surface gives a push needed to transport the other solutes. So organic nutrients would be reabsorbed by secondary active transport, which means they are co-transported with sodium, and that would include glucose, amino acids, some ions, and vitamins. We also have passive tubular reabsorption for water. So the movement of sodium and other solutes is going to create an osmotic gradient for water, and water will be reabsorbed by osmosis. That would be aided by those aquaporins, water-filled pores. So we get some obligatory water reabsorption. The aquaporins are always present in the proximal convoluted tubules, and then we get facultative water reabsorption. We insert aquaporins in the collecting ducts, and that happens if the hormone, antidiuretic hormone or ADH, is present. Solute concentrations in the filtrate are going to increase as water is reabsorbed. That creates concentration gradients for solutes, and that drives their entry into tubule cells and peritubular capillaries. Fat-soluble substances, some ions and urea, we're going to follow water into the peritubular capillaries, and they would be moving down their concentration gradients. So lipid-soluble drugs and environmental pollutants are often reabsorbed even though we may not want them to be. So at the basolateral membrane, sodium is pumped into the interstitial space by sodium-potassium ATPase, and active sodium transport concentration gradients will then drive downhill sodium entry at the apical membrane. Reabsorption of organic nutrients and certain ions by cotransport at the apical membrane. Reabsorption of water by osmosis through aquaporins, and that can increase the concentration of solutes that are left behind, and those solutes can then be reabsorbed as they move down their concentration gradients. And lipid-soluble substances diffuse by the transcellular route. They are not impaired by the cell membrane. If they are lipid-soluble, they can pass through the cell membrane, depending on size. Various ions and urea are going to diffuse by the paracellular route. So if we're transporting materials using a receptor, we have to deal with something known as a transport maximum. So you cannot transport more materials than you have receptors for. So transport maximum exists for almost every reabsorbed substance, and it reflects the number of carriers in the renal tubules that are available. When carriers are saturated, the excess has to be excreted in the urine. And this is what happens when diabetic patient has hyperglycemia. So if you have a lot of glucose in your blood, there will be a lot of glucose in the filtrate, and the amount in the filtrate will exceed the ability to pull that glucose back into the blood, so you'll end up with glucose in the urine. Reabsorption of the renal tubules and the collecting ducts. In the proximal convoluted tubules, we get most of the reabsorption. All the nutrients, glucose, amino acids are reabsorbed here. About 65% of the sodium and water are reabsorbed here. Many ions, almost all the uric acid, and about half the urea, which the uric acid and the urea we want to get rid of, so we're going to have to do that when we get into secretion. So in the nephron loop, the descending limb will allow water to leave, but solutes not. In the ascending limb, water can't leave, but solutes can. The thin segment is passive to sodium movement. Thick segments has sodium, potassium, chlorine symporters, so they move in the same direction, and sodium hydrogen ion antiporters that are going to transport sodium into the cell. And some sodium can pass into the cell by paracellular routes in this area, the ascending limb of the nephron loop. The distal convoluted tubule and the collecting ducts, reabsorption is going to be controlled by hormones. Antidiuretic hormone, which was released by the posterior pituitary gland, will cause the principal cells of the collecting ducts to insert more aquaporins in their apical membranes, and that will increase water reabsorption, and increased ADH levels would then cause an increase in water reabsorption. Aldosterone targets collecting ducts, the principal cells of the collecting ducts, and the distal convoluted tubule. Promotes the synthesis of apical sodium and potassium channels and the basolateral sodium-potassium ATPases for sodium reabsorption, and water would then follow them. As a result, very little sodium leaves the body. Without aldosterone, the daily loss of filtered sodium would be about 2%, and that is too much for us to survive. So the aldosterone's function is going to increase blood pressure and decrease potassium levels. Atrial natriuretic peptide from the heart reduces blood sodium, resulting in decreased blood volume and blood pressure. It's released again by cardiac atrial cells, and that is in response to high blood volume or pressure. Parathyroid hormone also acts on the distal convoluted tubules to reabsorb more calcium. So I would again encourage you to go through each of these figures in your text rather than me reading them to you. And that brings us to secretion. So tubular secretion is really reabsorption in reverse. Almost all of it occurs in the proximal convoluted tubules. The selected substances would be moved from the peritubular capillaries through the tubular cells into the filtrate. So potassium, hydrogen ions, ammonia, creatinine, organic acids and bases, and substances that have been synthesized in tubule cells would also be secreted. Bicarbonate ion. So tubular secretion is moving materials from the capillaries to the filtrate to make it part of the urine. Tubular secretion is important for disposing of substances such as drugs or metabolites that are bound to plasma proteins. Also helps to eliminate undesirable substances that were passively reabsorbed, the urea and the uric acid, for example. Helps to get rid of potassium, that's called the aldosterone effect, and that helps control blood pH by changing the amounts of hydrogen ions or bicarbonate in the urine. And here is your summary of reabsorption and secretion. And again, I would encourage you to look that over in your text. And we're going to stop there. And next we'll go on to regulation of urine concentration.